Good morning students. Today is the lecture 3 of module 1. In today's lecture we will cover basics of polymers, then polymers used in membrane preparation. Few polymers we will discuss which are most widely used in industries to prepare polymeric membranes such as cellulose acetate, polyamide, polysulfone and other polymeric materials. Then we will try to understand their basic properties and advantages and disadvantages of using such polymers for membrane preparation. So, why I am trying to cover polymers, basics of polymers is that one need to understand the various properties of the polymers, how the polymers are actually manufactured, what is their source, what are their different advantages and disadvantages. So, that when somebody try to prepare a membrane in a lab scale using polymeric materials, this knowledge will help you to understand and to fix the which polymer to be utilized for preparing a particular membrane for a particular targeted desired separation of course. So, more than 130 materials have been identified till date to prepare membranes. However, only very few have achieved commercial status and lesser than that have obtained regulatory approval for use in food, pharmaceutical and other kindred applications. Now, the reason is that most of the polymers have their even why to talk about polymers. Today's lecture of course we are talking about polymers. We will next lecture we will cover our inorganic and ceramic materials. So, let us restrict our discussion to polymers. So, I was telling that why only very few were used commercially and only very few has obtained regulatory approval. The reason is that every polymer is very unique by nature of their inherent properties. So, to suit a particular application, one particular polymer properties has to meet the standards of the separation which you want to actually use. So, there are inorganic materials also for preparing membrane. So, today's lecture as I told we will only focus about polymeric materials. So, there are two types of different polymers exist, one is natural polymer, another is synthetic polymer. So, we will discuss about these things slowly. So, natural polymers. So, natural polymers occur in nature as the name suggests itself and can be extracted from plants and animals and mostly they are often water based. So, natural polymers they are essential to daily life as our body usually and human forms, all sorts of human forms and even animal forms are based on them. So, some of the examples are silk, wool, DNA, cellulose and proteins. So, starch is a natural polymer that is made up of hundreds of glucose molecules. Similarly, natural rubber is a polymer obtained from the latex of the rubber tree. Now, you may be aware that rubber is also made synthetically. So, then synthetic polymers are derived from petroleum oil and made by scientists and engineers. So, they can be classified into 4 different categories. So, thermoplastics, thermosets, elastomers and synthetic fibers. So, they are commonly found in a variety of consumer products and we use them in our daily life every day. So, examples are nylon, polyethylene, polyester, Teflon and epoxy. So, let us discuss some of the basics of the polymers. So, polymers are high molecular weight components built up from a number of basic units, the monomers. The number of structural units linked together to form a long chain molecule is defined as the degree of polymerization. The molecular weight of long chain molecule is dependent on the degree of polymerization and on the molecular weight of the basic unit, that is the monomer. So, in a nutshell we can understand that when several monomers join together it becomes a polymer. Of course, how they join, how they fuse with each other, whether it is a single monomer or there are different types of monomer that are fused together to get a polymer. So, these are of course different issues to be addressed and dealt differently. So, for example, the simplest polymer is polyethylene. So, all of us knows this and we use it in our everyday life. So, which is obtained from the ethylene or ethene, the IUPAC name is actually ethene. So, on polymerization the double bond of ethene, that CH2 double bond CH2 is opened up and a large number of C2H4 is coupled together to form a chain which is linear in case of a polyethylene. So, it is a linear molecule polyethylene and 4 valences of a carbon atom forms a tetrahedron. The angle between the CC bonds is usually 109.5 degree. The CH2 unit is called the segment, and with increase in number of segments, the physical, chemical and mechanical properties of the polymer changes. So, when we increase the number of segments, okay, so the properties of the polymer changes. So, we will see how it actually. So, let us see this example of polyethylene. When the number of units is only 1, its molecular weight is 28 and the its characteristic features at 25 degree centigrade is that it behaves as a gas. When we increase the number of units to 6, the molecular weight increases to 170 and it behaves as liquid. Further, when we increase the number of units to 200, so the molecular weight jumps to 5600 and its characteristics features becomes like wax. Then again we increase to 750 or 5000 or more than that. So, their molecular weight just keep on increasing, okay, and they become plastics. So, as you can understand from this particular table, when the number of units are we are increasing the number of units for a particular polymer. So, their molecular weight is increasing as well as their properties are also changing. So, from gas to liquid, liquid to wax and then wax to plastic. So, based on the nature of repeating unit, polymers can be classified as homopolymer and copolymer. So, when repeating units of the polymer are same, then it is a homopolymer. So, polyethylene is the best example of this thing. So, all the monomers of the polymer are of same nature and origin. So, copolymer, when the repeating units are different. So, that means two monomers A and B are coupled together in various ways and number of different structure can be distinguished. So, copolymers are obtained by copolymerization of two monomer species are sometimes called bipolymers when the monomer species are 2. So, those obtained from 3 or 4 monomers are called terpolymers and quaterpolymers respectively. There are different types of copolymers exist. The first one is random copolymer, the second one is block copolymer and the third one is graft copolymer. So, what is random copolymer? So, when the sequence of structural unit is completely irregular, the copolymer is said to be random copolymer. So, the properties of random copolymer strongly depends on the molar ratio of both the monomer units A and B. So, a classic example is the synthetic rubber, which is NBR, the nitrile butadiene and butadiene rubber, or SBR, the styrene butadiene rubber, EVA, ethylene vinyl acetate copolymer, or EVAL, ethylene vinyl alcohol copolymer. So, the next type of copolymer is a block copolymer. Here the chain is built up by linking blocks of each of the monomers. So, one example is SIS, which is styrene isopropyl styrene. So, the next is graft copolymer. Here the irregularities occur in the side chains rather than the main chain. So, the second monomer is attached to the main chain by chemical means or irradiation. So, typically the main chain is formed from one of the monomer and branches are formed from another monomer, and the side or else the side chains have constitutional or configurational features that differ from those in the main chain. So, basically two different nature of monomers are fused together to get a graft copolymer. So, let us have a look to this particular image where you can see that the different structures of polymers. So, the homopolymer you can see there only single monomer type, all are single type of monomer. In alternating copolymer, so we have one type of monomer which is A followed by different monomer which is B, then again A, again B. So, it goes in a sequence. So, it is a random copolymerization. So, A and B are fused together randomly. So, there is no particular sequence that is followed. Here in this particular case you can see there are 5 monomers of B fused together followed by 5 monomers of A. So, again this sequence will repeat. So, this is called block copolymer, and in graft polymer you can see the two different types of monomers are fused together. However, they are joined by grafting. So, here the B monomers are grafted to the monomeric chain of A. So, the polymers can be either linear or they can be branched. The linear looks something like this, and if it is branched, then they can be grafted to both any one of the side of the monomeric chain, and when it is cross linked, so the structures look something like this. It is also possible to connect two or more chains to each other by means of cross linking. So, cross linking occurs by two methods, one by chemical reaction, another by physical cross linking. We will discuss little more about the basics of polymers. So, let us understand what is stereoisomerism. So, a very important class of polymers are vinyl polymers, which are obtained by polymerization of vinyl components, that is CH2, CHR. The most simplest one is polyethylene, okay, where only hydrogen atoms are attached to the carbon main chain. So, vinyl polymers are characterized by CH2, CHR repeating units, where the side group is different from the different polymers. Let us look at this table. This is telling us about different vinyl polymers. So, for polypropylene, the R group is CH3, for polybutylene the R group is C2H5, for polystyrene it is C6H5, similarly for polyvinyl alcohol it is OH, for vinyl chloride it is Cl. So, polymethyl crylate it is CH2, this CCH, CH3 which is methyl methacrylate, okay, and for polyvinyl pyrrolidine this is the repeating unit. So, the side group R can be attached to the carbon atom in two different ways, either in the form of D or L form. So, you can read little more about these basics from any polymer textbook. And here we are just I am trying to just give you a little understanding about the basics fundamental of polymers, then we will quickly move to different types of polymers which are utilized for the preparation of membranes. So, three different arrangements may be distinguished in the polymer. So, the first is called isostatic, the second one is syndiotactic, and the third one is called atactic. So, what is isotactic? So, here all the side groups are lie on the same side of the main chain. You can see all the R's are lying on the same side of the main chain, nothing is lying here on the bottom side. So, this is isotactic. In syndiotactic, the R groups are placed on the alternate sides of the main chain. So, one here followed by one here, okay, then one here again followed by one here. So, this is alternate arrangements, and in atactic the side groups are randomly arranged along the main chain. So, there is actually no proper sequencing followed. So, you can see here there are three arrangements followed by another one. So, it can be anything. So, it is basically random, they do not follow any proper sequence. So, the position of the side group R has a very important influence on the polymer properties, since crystallinity depends on the regularity of structure. So, crystallinity is a very important feature of the polymers. So, isotactic polymers may be very crystalline, whereas atactic polymers are non-crystalline. So, most of the atactic polymers are non-crystalline. So, crystallinity not only affects the mechanical properties of the polymer, but also affects its permeability. As you know, the permeability is one of the most important feature of the membranes. So, crystallinity and permeability both are very important for a polymeric material. So, the choice of polymers as membrane material is not arbitrary, but based on a very specific properties originating from the structural parameters. So, that is what I was telling in the beginning of the class, that which polymer to be chosen for a particular separation or for a particular targeted application, it is to be decided based on so many things. First is what material you are going to separate, the solute basically or the solvent, and what type of membrane material you will decide, so that there will be more interaction between the membrane and the solute or solvent that is going to be separated, and how the properties of the membrane will affect the separation. So, that is why we are trying to understand the properties of the different polymeric materials, and in the next class we will understand the properties of the ceramic materials. So, the structural parameters determine the chemical, thermal and mechanical properties of polymer. Structural parameters are molecular weight, chain flexibility and chain interactions, these three. Let us understand what is chain flexibility. So, chain flexibility is determined by two important factors. The first one is the character of the main chain. The second one is the presence and nature of the side chains or groups. So, basically two things. The first one is the first monomer, which consists of the main chain, and the second one is the another monomers which we are going to graft or getting cross linked to the main chain, which is called a side chain basically. For example, in polymers such as vinyl polymers, the main chain consists entirely of CC bonds. Okay. The rotation around CC is possible, which makes the chain rather flexible. However, when main chain is completely unstructured, unsaturated, no further rotation is possible. As a result, a very rigid chain is obtained. When the rotation is possible, the chain becomes flexible, rotation of CC bond. When the main chain becomes completely unsaturated, so no more rotation can be possible. So, as a result, very rigid structure is obtained. So, introduction of heterocyclic and aromatic groups into the main chain leads to a substantial decrease in flexibility. So, how you increase the flexibility of a particular polymer? So, you can introduce some of heterocyclic or aromatic groups to the main chain. So, the degree of flexibility increases. So, this type of polymers show excellent thermal and mechanical stability. For certain membrane application, you need to have excellent thermal and mechanical stability. Okay. So, for this you can impart some of the heterocyclic and aromatic groups to the main chain, so as to increase the flexibility. So, chain flexibility is determined by the character of the side groups, which determines whether rotation around the main chain can take place readily or whether steric hindrance occurs. So, the side chain actually deciding whether rotation is possible or not. The character of the side group has strong effect on the interchain interactions. The smallest possible side group is the hydrogen atom. The hydrogen is the smallest possible side group that can be imparted to the main chain. So, this has no influence in the rotational freedom of the bonds in the main chain, and its effects on the interchange distance and interaction is also very minimal. So, on the other hand, if there is a phenyl group C6H5, then it reduces the rotational freedom of the main chain, while the distance between the various chain is also increased. So, the next parameter is molecular weight. So, the chain length is an important parameter in determining the properties of a polymer. The molecular weight is an important property relative to membrane preparation. The membrane average molecular weight is given by Mn equals to Ni summation of Ni Mi by summation of Ni. So, Ni is the number of molecules with average molecular weight Mi. The weight fraction Wi is used to calculate the average molecular weight. So, molecular weight is the summation of Wi Mi divided by summation of Wi. So, with increasing chain length, number of interaction sites between various chains increases, and consequently the chemical, physical and mechanical properties of the polymers varies. So, this we have seen in one of the table where I was showing you when the chain numbers increases, when the number of units increases, how the properties and the molecular weights are differing. So, in linear and branched polymers, only secondary interaction forces between the different chains exist, whereas in network polymers the various chains are bound to each other covalently. Secondary intermolecular forces are considerably weaker than the primary covalent bonds. However, they have a strong effect on the physical properties of the polymer because of the large number of interactions that is actually possible. So, three types of secondary forces can be considered. The first one is dipole forces, which are also called as Debye forces. The second one is called dispersion forces, also known as London forces, and the third one is the hydrogen binding forces. Here in the table you can see there are different types of forces, and their kilojoules per mole is also given the energy. So, covalent, ionic, hydrogen bonding, dipole and dispersion. You can see covalent is the strongest in terms of the energy, and dispersion is the smallest. So, student, let us try to understand what is the state of polymer. Now, the state of polymer can be defined as the phase in which the polymer appears. The selection of a material for certain application involves different criteria. The choice of polymer is not that important when porous membranes are actually considered in terms of separation, but it certainly affects its chemical, thermal and other properties such as absorption and wettability. Additionally, the choice of cleaning agent is also determined by the choice of polymer. So, what is the meaning of that? So, in one of the classes I told you when the continuous separation is happening, then the solutes are getting deposited on the surface of the membrane. So, when this is increasing, the concentration polarization increases, the layer becomes cake and some of the solutes gets inside the membrane pores. So, thereby making two types of fouling possible, one is external fouling and internal fouling. So, when the membrane gets fouled, we need to clean it. So, the easiest way of cleaning is back flushing. So, you use water and back flush the membrane from the back side of the membrane, you flush it. So, the pores will get clean, but many times it happens that the pores are not getting cleaned due to strong interaction of the solute molecules along with the membrane material. So, you need to use some organic solvents, some acids, dilute acids, some alkalis or some other solvents to clean it. So, this type of solvents may swell the membrane material. So, that is why it is very important that the choice of polymer also determines or governs the choice of cleaning agent. So, when dense membranes are considered, the polymeric material chosen directly influences the membrane performance and especially glass transition temperature and crystallinity temperature, especially when there are no pores, non-porous membranes. So, let us understand what is actually here this one glass transition temperature is. So, it is one of the most important properties of the polymeric materials. So, when a non-crystalline or amorphous polymer is heated, a temperature exists, okay, at which polymer changes from glassy to rubber state. Okay. So, the figure below demonstrates the variation in the tensile module E of a completely amorphous polymer as a function of temperature. You can see Tg. Okay. This is actually the glass transition temperature, and glassy states, the change of glassy state to rubber state happening at which temperature is known as the glass transition temperature. So, the IUPAC definition suggests that the process in which a polymer melt changes on cooling to a polymer glass, or a polymer glass changes on heating to a polymer melt. So, effect of polymeric structure on glass transition temperature. Now, the physical properties of a polymer are determined to a large extent by the chemical structure. So, the thermal motion of the polymer chains is dependent on the ability to rotate around the main chain. So, this is mainly determined by two factors, chain flexibility and chain interaction. So, an aliphatic polyamide has a much lower glass transition temperature than that of a aromatic one. As for example, linol 6 has a glass transition temperature value of 50 degree, while Nomex has a glass transition temperature of 273 degree centigrade. So, this table gives the glass transition temperature for various vinyl polymers containing different side groups. Now, let us discuss about the membrane polymers. So, there are two different types of membrane polymers can be classified. One is based on porous membrane structures, another is dense or non-porous membrane structures. So, porous are basically your microfiltration, ultrafiltration, and non-porous membrane is that is used for your gas separation and pervaporation. So, porous membrane. So, porous membrane contains fixed pores in the range of 0.1 to 10 micron for microfiltration and 2 to 100 micron for ultrafiltration. Now, the selectivity is determined by the dimensions of the pores, but the choice of material affects the phenomena such as adsorption and chemical stability under certain actual conditions. Now, the main problem in microfiltration and ultrafiltration is the flux decline. This we have discussed in last class. Therefore, the choice of membrane material for such process is based on prevention of fouling and cleaning procedure after it is fouled. So, frequently used polymers used in microfiltration membrane are polycarbonate, polyvinylidene fluoride, so which is PVDF, then PTFE, polytetrafluoroethylene, polypropylene, polyamide, polysulfone, polyethyramide. So, there are many others also. So, these are some of the polymers which are actually commercially being used. And let us see about non-porous membranes. So, non-porous membranes are primarily used for gas separation and evaporation. So, the choice of material is determined by the type of application, and the polymer type can range from an elastomer to glassy material. So, now we will see and discuss about the few polymeric materials which are widely used for preparing membranes. So, we will let us start with cellulose, which is the most abundantly available natural material on earth. For membrane preparation, despite of excellent thermal and chemical stability of hydrophobic polymers are more favored as membrane material because of the reduced adsorption tendencies. So, hydrophobic materials polymers are more widely used because their adsorption tendencies towards solute will be very less. So, that the deposition of the solutes on the surface of the membrane as well as the consequent fouling will be less. So, the adsorption of solutes has a negative influence on the flux because the adsorbed layer presents an extra resistance towards mass transfer and consequently contributes to a decline in flux. So, the another resistance which we have discussed earlier also, one resistance that is inherent is due to the membrane thickness. The second resistance is coming due to the adsorbed layer on the surface of the solute. Lesser is the thickness of the adsorbed layer, the lesser will be the resistance towards mass transfer. So, the best known class of such polymer is cellulose and its derivatives such as cellulose esters. So, these include cellulose acetate, cellulose triacetate, cellulose triproportionate, ethyl cellulose, cellulose nitrate and mixed esters such as cellulose acetate butyrate. So, cellulose and its derivatives are used in microfiltration and ultrafiltration as well as in reverse osmosis, gas separation and dialysis membranes. So, what is cellulose? Cellulose is a polysaccharide and can be obtained from plants. Its molecular weight usually ranges from 500,000 to 1,50,000. implying that the number of segments are roughly between 3000 to 9000. So, as we understand the number of units increased, the molecular weight also increases. The glucose segment contains 3 hydroxyl groups which are susceptible towards chemical reaction. So, and forming esters. So, cellulose ester and cellulose nitrate and ethers, ethyl cellulose. The glucose repeating units are connected by the beta 1,4 glycosidic linkage. Cellulose is crystalline in nature because of its regular linear chain structure. Although this polymer is hydrophilic, it is not water soluble. So, cellulose or regenerator cellulose is mainly used as a material for dialysis membrane. The next one is cellulose acetate. You can see the structure of cellulose acetate here in the top corner. So, cellulose acetate is one of the widely used materials for asymmetric membrane production. It is derived from cellulose via acetylation process. It is employed for reverse osmosis, nanofiltration, microfiltration and ultrafiltration membranes. So, cellulose acetate is a classic membrane material used by pioneers of modern membrane technology to create skinned membranes. So, as you know, we have discussed what is skin membranes. So, one top layer that is fused along with a porous layer, and that top layer is actually called skin membranes, mostly the asymmetric membranes. So, cellulose acetate is prepared from cellulose by acetylation, that is reaction with acetic anhydride, acetic acid and sulfuric acid. So, let us understand what are the different advantages and disadvantages of cellulose acetate. Now, the advantages is hydrophilicity. So, the more the material will be hydrophilic, the fouling will be less. Okay. So, wide range of pore size can be manufactured from RO to microfiltration with reasonably higher flux. It is very easy to manufacture and the cost is of course low. But it has certain disadvantages also. The first disadvantage that it has narrow temperature range. It cannot withstand higher temperature. The temperature which can be utilized using this membrane is between 30 to 40 degree centigrade. Although under carefully controlled operating conditions, you can go little beyond that. And another disadvantage is that narrow pH range. So, most of the cellulose acetate membranes are restricted to pH 2 to 8 and few can go to 3 to 6, and the polymer hydrolyzes under acidic conditions, whereas highly alkaline condition causes deacetylation. So, then the cellulose acetate will go back to cellulose actually, and which eventually affect the selectivity, integrity and permeability of the membrane. So, other disadvantages of cellulose acetate is that its poor resistance to chlorine. So, many times chlorine is present in water and wastewater. So, when you are using a cellulose acetate for such treatment, water or wastewater treatment, then the presence of chlorine actually will create problem for this type of membranes. And cellulose acetate is reported to undergo creep. So, creep is a compaction phenomena, okay, and its compaction or creeping is is slightly greater than other polymeric materials. So, that is the gradual loss of membrane properties under high pressure over its operating lifetime. Cellulose acetate is highly biodegradable. This is another big problem when if at all you are using this type of membrane for some bioremediation or wastewater treatment process, or in using it for some production of some biopharmaceutical drugs. So, it is highly susceptible to microbial attack due to the nature of its cellulose backbone. So, microbes will actually try to eat the cellulose as a source of glucose for them. So, cellulose acetate has poor storage properties. So, the next class of membrane which is widely used is called polyamides, PA. So, these polymers are characterized by the CONH groups. So, the repeating unit is CONH. So, aliphatic polyamides comprise a very large class of polymers, and the aromatic polyamides are preferred as a membrane material because of their outstanding mechanical, thermal, chemical and hydrolytic stability as well as perm selective properties. And the aliphatic polyamides show good chemical stability. For example, linol 6. Linol 6 is a very good material for preparing membranes, and the properties of aromatic polyamides are determined by the aromatic groups in the main chain, which considerably reduces the chain flexibility. So, aromatic polyamides have a glass transition temperature of 280 degrees centigrade and even higher than this compared to the values less than 100 degrees for the aliphatic polyamides. So, aromatic polyamides consist of meta substituted ring. Under these circumstances, the crystallinity also increases for the polymer. So, these para-substituted polybenzamides can be produced as super fiber because of their high tensile strength obtained after chain orientation in the fiber direction. As membrane material, these polymers had little interest. Example is Nomex, which is polyamphenilyl isothalamide. So, let us look the properties of nylon 6 and Nomex. You can see that Nomex has a higher glass transition temperature than nylon 6, and its melting temperature is also higher than that of the nylon 6, and its water absorption capacity is also higher. So, these are the structures of Nomex and nylon 6. And let us understand what are the advantages and disadvantages of polyamides. So, the advantage is wide pH tolerance compared to cellulose acetate. So, you can use it without any hindrance for different water wastewater treatment processes, and disadvantage is again poor chlorine tolerance, and it is prone to biofouling, and polyamide forms contact skin layer in many composite membranes. So, actually when we are preparing a composite membrane using a polyamide, so it will form another types of skin layer in the composite membrane itself, thereby providing an additional resistance to already existing resistance. So, the next class is widely used in membrane preparation is polysulfons or its derivatives, which is polyether sulfon, PS or PES. So, the polysulfons possesses very good chemical and thermal stability. So, these polymers are widely used for ultrafiltration membranes and as support materials for composite membranes. So, most of the ceramic based composite membranes uses polysulfons or polyether sulfon to impart the top or skin layer on the surface of the ceramic membranes, whereas the ceramic membrane is used as the support. The SO2 group in the polymeric sulfon is quite stable because of the electronic attractions of resonating electrons the adjacent electronic groups. So, this is the polysulfon structure, and the advantages is that it can withstand wide temperature limits, so almost up to 125 degree centigrade, and the tolerance limit of the polysulfon membranes for pH is very wide, 1 to 13, fairly good chlorine resistance, up to 200 ppm chlorine it can withstand. So, for cleaning purposes this type of membranes will have no problem while it deals with chlorine, and it is easy to fabricate, wide range if pore size available for ultrafiltration and microfiltration applications. So, we can easily prepare either multi microfiltration or ultrafiltration membranes using polysulfon material. So, good chemical resistance to aliphatic hydrocarbons, fully halogenated hydrocarbons, alcohols and acids. So, this means that polysulfons have extreme good chemical stability towards most of the chemicals and solvents. However, it does not offer much resistance to aromatic hydrocarbons such as ketones, ethers and esters. Its disadvantage is that it has very low pressure limits. So, typically around 700 bar when you use polysulfon membrane as a flat sheet membrane, or 25 bar when you use them as hollow fiber membranes. So, often it happens that we use pressure much higher than 25 or 30 bars. So, in that those applications it is difficult to use polysulfon membranes. So, another disadvantage is hydrophobicity, so which leads to apparent tendency to interact with a variety of solutes, making it prone to fouling in comparison to more hydrophilic polymers such as cellulose and regenerated cellulose. So, the next class is PVDF, so polyvinylidene fluoride. So, it can be autoclaved. So, this is the beauty of PVDF membrane, and its chemical resistance is to common solvents is extremely good. So, it is a very popular membrane for manufacturing of microfiltration and ultrafiltration, and it has better resistance to chlorine than all other polymeric materials. So, commercially used for fruit juice clarification because of its resistance to limonene. Limonene is the substance which is present in most of the fruit juices. So, this is the structure of PVDF. The next class is PTFE, which is called polytetrafluoroethylene. So, it is also very stable with strong acids, alkalis and solvents. It can be used at wide range of temperature. Usually, it can withstand up to 260 degree centigrade temperature. It can be made by a combination of heating and stretching melted film, which results microfiltration sized pores. It is easy to fabricate also. It is extremely hydrophobic in nature. So, the adsorption of solutes due to its hydrophobic nature will be more, and commercially used for treatment of organic feed solution, gas and vapors. The next class is polypropylene PP. The polypropylene can be made by thermal inversion process and also by melt extruding and stretching. It is widely available in the form of hollow fibers, and it is hydrophobic, relatively inert, and can withstand moderately high temperatures. So, the next class is regenerated cellulose. So, you can see the regenerated structures here. So, this is actually the structure of the cellulose, to which we are adding CH2, sodium hydroxide, and water is getting out of this reaction. So, thereby we are impacting different types of this sulfur groups here, okay, to increase its different properties of the cellulose. So, that is why it is called regenerated cellulose. So, they are extremely hydrophilic and have exceptional non-specific protein binding properties. So, this class of membrane material is extremely good to prepare membranes of microfiltration or ultrafiltration range, where the application is protein separation. So, it has also good resistance to some common solvents such as butanol and ethanol. So, it can almost tolerate 70% of both butanol and ethanol concentration. So, it can tolerate temperature up to 75 degrees centigrade, which is actually lower as compared to other polymeric materials. You can refer, these are the text and references books, as after every lecture I am showing this. So, Mulder is the most important textbook for this particular course. So, you can refer to that apart from other books also. So, thank you very much, and in the next class we will be discussing about the inorganic materials for membrane preparation, their properties, advantages and disadvantages. So, with that, in the next class we will wind up our different membrane materials, and the next class we will start how membrane can be prepared using different techniques. So, thank you very much.